All right, a few quick examples to talk about equivalence classes and partitions. So for the first example, we have the set here, 1, 2, 3, 4, 5, and 6. And you can see P here is a partition of that set. We have the elements 1, 3, 4 in the first subset of our partition, 2, 5 in the second subset, and 6 is the third subset of A, and it is an element of our partition. Okay. So we just want to quickly define an equivalence relation so that the equivalence classes of R are the elements of P. Okay. So we just need to write down what R is. Remember, R is a relation, so that means it's a subset of A cross itself. And we just need to write down all of the pairs of elements that are related to each other. So let's start with the first element of our partition, we can think of as the first equivalence class in our relation. Well, we need everything is related to itself. 1 is related to 1, 3 is related to 3, 4 is related to 4. We also have 1 is related to 3. 1 is, let's do actually the symmetric thing first. Let's do 3 is related to 1, just to keep things in the same order. Then we have 1 is related to 4, 4 is related to 1, and we have 3 and 4. 3 is related to 4, 4 is related to 3. So they're everything from our first element of our partition, first subset of A in that partition. Okay, let's do the next one. Do that in blue, I guess. Okay. So then we have, 2, 2, 5, 5. And we have 2 is related to 5, and 5 is related to 2. So they're everything that comes from that second element of our partition. And then finally, the third element, mark that in green, I guess. That one's easy. That's just 6 is related to itself. And that is it. So that wasn't too bad to define an equivalence relation given a partition. Very straightforward. Let's look at a digraph to see how this looks. So I'm going to put a 1. I'll do it like this. 1, 2, 3, 4, 5, and 6. So here's our digraph. And you can kind of see the equivalence classes in the digraph. So here we have 1 is related to itself. 3 is related to itself. 4 is related to itself. We'll put the other ones in later, but just to show you what these equivalence classes look like, we'll just start with these. We have 1 is related to 3 and vice versa. We have 3 is related to 4 and vice versa. And we have 4 is related to 1 and vice versa. So we have kind of a nice complete-ish graph here. Double-sided, everything's related to itself, and every element in our partition or in our equivalence class is indeed related to each other. So that's what that looks like. And I'll switch the colors of the arrows just to explain the different equivalence classes. We have 2 and 5 are related. So we have 2 is related to itself, 5 is related to itself, and 2 and 5 are related to each other in both directions. That's the second equivalence class. And again, everything in the equivalence class you have related to itself. Of course, everything's related to itself in an equivalence relation. And every element in that equivalence class is related to each other. And then finally, we just have 6 by itself in its own equivalence class. 6 is related to itself. So that's pretty cool. As an aside, if you did have an equivalence class that had 4 elements, let's say these were the 4 elements, what it would look like is that you'd have everything related to itself in the diagram, and you would have each element related to each other element. So it would look like, we'd call it a complete graph. Every possible connection is made with both directions. So let's say maybe you had some other elements in your set. This would be an equivalence class if there was no element also related to these guys. This is what an equivalence class would look like if the equivalence class had 4 elements, these 4 elements. So that's kind of just an idea there. Let's move on to the next example, and maybe you guys should try this one. Our set now is the integers without 0. So positive and negative natural numbers, but no 0. We want to define a relation R on the set A, on the integers without 0, where 2 elements are related, if and only if when you multiply them, you get something greater than 0. So, what I want you guys to do is determine the equivalence classes of R, figure out what's in the equivalence classes, and then describe in words, if you can, how this partitions our set. I think a good way to start is pick any old element you like in A. Maybe pick 1, for example. Find the equivalence class of 1. And the reason I picked 1 is just because it's a really easy number to think about multiplicatively. Okay, so pause the video now. Try that yourself. Okay, now that we're back, well, the equivalence class of 1 is going to be all elements in A such that they're related to A, so that A is related to 1. Or, well, we know what that means. It means that A times 1 is greater than 0. So this is what we need. A times 1 is greater than 0. So what elements in the integers, not including 0, give us this? Okay. Well, if you think about it, as long as A is positive, then A times 1 will, of course, be positive. Multiplying by 1 does nothing. Okay, so the set is just going to be, in fact, we know what it's going to be. It's going to be all positive natural numbers. And we have a name for that set. It is indeed the natural numbers, which is, of course, 1, 2, 3, all the way to infinity. So that's the equivalence class of 1 and the equivalence class of all positive numbers. Remember, you can pick any representative in an equivalence class and it'll behave the same way. Excellent. So let's pick a number not in that equivalence class and figure out what the equivalence class of that is. How about negative 1? Okay, same idea. We need that's all A in A such that A times negative 1 is greater than 0. Well, all that means is, of course, we need A to be negative. So this is going to be the set negative 1, negative 2, negative 3, all the way to negative infinity. So there are 2 equivalence classes. Did that capture all of the elements of our set A? It did. All of the positive elements are here. All of the negative elements are here, and that's all of them. So our partition is, well, it's the set of positive integers in our first element and negative integers in our second element of our partition. Or you could think of these, of course, as equivalence classes. Remember, partitions and equivalence classes are the same thing. All right, and that is talking about how partitions and equivalence classes relate to each other.